I just discovered something disastrous. These ones I ended up with are pretty underwhelming quality. You can see the reflection changing when I spin it. And yeah, I guess it works. A section of this video is sponsored by PCBWay. Last episode I made this beautifully smooth gantry, so I guess it's time to install the stepper motors and get the thing moving. Welcome back to my fully enclosed laser engraver / cutter, the second series where I knowingly execute a disadvantageous design because I dug myself into a hole I cannot, or maybe don't want to, get out of, because doing so would mean nuking everything to start from scratch. After seeing how incredibly smooth those linear rails are, I definitely regret having designed the entire machine around crappy stepper motors driving lead screws instead of the ubiquitous NEMA 17 belt drive. Last video I said I couldn't fit any NEMA 17 on the carriage due to space constraints. Let me demonstrate. So this is the back of the machine. The panel for enclosing it is gonna screw right on top of these. So if I just stick in the motor it was designed for, see how much clearance there is? Just about 2 millimeters. Now try to fit a NEMA 17 in that gap. There is no way to fit anything other than these super thin pancake steppers, which are guaranteed to be totally inadequate to push around a carriage this heavy. But someone in the comments had the obvious solution. Why don't you just make it Core XY? And honestly, I have no idea why I didn't think of this myself. I even considered making a potential future successor machine Core XY, but not this one. In any case, it would definitely solve the problem by putting both motors behind this plate where I have ample space available, running the belt through a hole to drive the laser head remotely. And that's exactly what I plan on doing for the revised version of this machine I'll eventually publish. However, doing this here would mean mounting the stepper motor where it blocks access to this bolt, ignoring all these holes I spend hours meticulously drilling in the exact place they should be, just to butcher the existing carriage in order to install idlers where there were never meant to be any, and then find out my frame isn't actually up to the task of supporting the belt tension for any prolonged period of time and starts bending after a while. It's really a problem of sunk cost. At this point, I'm 95% done and just need to install the damn lead screw, whereas belts would mean either starting from scratch or ending up with a cobbled together mess of a machine, which the OCD in me totally balks at. In other words, I'd rather stick to bad motors than ruin a good design of a bad solution by botching in good motors and a bad design fix. Because realistically, what's the specific disadvantages of having lead screws in this case? Yes, there is greasy threaded rods hanging around to bump into and dirty workpieces on. Yes, periodically having to grease the lead screws for maintenance is annoying, but it's not a 3D printer and it doesn't execute the same moves over and over and over, layer upon layer, so wear shouldn't be anywhere near as pronounced. Yes, the travel speeds are a bit slower. It might take a minute to home, and for a job where it has to jump around all over the place, drilling holes, it might take a little bit longer, but once again, it's not a 3D printer, and laser jobs don't take 12 hours anyway, at least not usually. And finally, yeah, I cannot move the gantry manually, powered or not. I'll have to click the buttons to move it around, which might become inconvenient for setting up jobs later on. Is that worth scrapping everything I did in the last video to go disappear behind the computer for a month redesigning everything? Not to me, so let's crack on. Also, forget everything I just said. We all know my decision making is way too compulsive for my own good, and I tend to follow through on things right to the bitter end, so just enjoy watching a different approach than the dull as dishwater timing belt direct drive. Shit. I'm gonna end up bending it like that. So this is M6 stainless steel thread rod I'm using for the lead screws. From what I learned converting my 3D printer to lead screws, I think it's your best bet when it comes to CNC projects on the cheap. It's a lot harder than mild steel, as I was vividly reminded when I almost ruined my saw trying to cut it off just now. Wow, that doesn't go in at all. So it'll be a lot more wear resistant, there is no galvanization to wear off, and it obviously doesn't rust. I also noticed the diameter of generic galvanized old thread is actually quite inconsistent, with rough spots in some places where the thread is slightly malformed. That's not an issue if you just want to thread on a nut, but when it's spinning at 1000 RPM, you probably don't want any rough spots. The stainless steel ones seem to be slightly better quality in that regard, though I was taken aback by just how expensive they are. They cost almost 3 times as much as the generic galvanized stuff. Anyway though, first step will be grinding down this end to fit inside the bearing. Now, my usual 5mm bearing blocks for spinning up stuff obviously won't fit, since they're literally the same size bearing, and I don't have a 19mm Forstner bit to make new ones for the 6mm ID bearing, so I simply 3D printed the new fixtures. And I did order a bag of slightly more expensive bearings, expressly with this purpose in mind, which seems to have paid off as they look reasonable quality. Now, I know you folks don't like when I use the cutoff wheel to grind stuff, but look, I'm only using the edge of the disc to grind, not the face. It's really no different than if I were using it to cut something apart. Also, I'm not sure what this brown cutting disc is made of, but it goes through stuff like butter. All the gray, pink, and white Dremel grinding bits, as well as the dark gray fiber reinforced cutoff wheels I have, all tend to lose about as much material themselves as they are removing from the workpiece when used on something as chewy as generic mild steel, which I guess could be down to them all being expired from being well over a decade old, but this brown disc remains amazingly aggressive. And this is actually key to the whole operation here, because by grinding only with the edge, I minimize contact area with the workpiece, and the disc cuts even more aggressively, which reduces the amount of pressure trying to deflect the spinning awl thread, and thereby hopefully helps mitigate any runout I might inadvertently grind into it. Not gonna lie, as much as I just praised the brown cutoff wheel, it's no match to the stainless. Saying the whole process was a royal pain in the ass would be an understatement. I was having the very problems I explicitly tried to avoid by using a sharper cutting disc. Namely, it tends to create a weird polygon shape instead of a smooth round peg like you'd expect. I also did the other side and ended up with a slightly triangular cross section in some areas closer to the thread. You can see the reflection changing when I spin it. Overall, 3 out of 10, I cannot recommend this poor man's turning method for stainless steel. Definitely try and stick to timing belts, and where that's not possible on a CNC router, go for the cheap galvanized threaded rod, or at least a design that doesn't require you to machine stainless steel. And ideally, just go and buy a proper lead screw if you can. In any case, the bearing should now be a reasonable press fit on this end of the screw. Probably not quite as tight as I would have liked, but again, I was having trouble getting it round and didn't want to deform the inner race of the bearing, so it'll do. That went about as well as I could have hoped. No idea how much of a difference popping it in the freezer overnight made, but the bearing's on there. So on the other side we need to couple it to the motor shaft, and my original plan was to just use a simple piece of plastic tubing, but since that didn't work out so well on my 3D printer, I figured I'd just buy a proper aluminum coupler with set screws. Now you can get these generic flexible ones in weird sizes too, including 3 and 4 millimeters, but at this diameter compared to the lead screw and motor shaft, it'll have a lot of inertia and act like a flywheel, needlessly screwing with my accelerations. So I ended up buying this much smaller but rigid shaft coupler on AliExpress, thinking I could maybe cut a few slots in it to make it flex. Problem was, this thing has dog water tolerances. One of the holes is almost 0.1 millimeters oversized, and possibly they're not even fully concentric. In any case, I always ended up with atrocious amounts of runout. And no, the shaft I used for testing is not undersized, it's just that loose of a fit, making the coupler kind of unusable. Now, I did open a dispute and promptly got refunded, so no harm done. Since I didn't have to send it back, we're just gonna try using it anyway by jamming something very thin in with the motor shaft to kind of fill the space and keep it centered. If that doesn't work, I'm just gonna have to 3D print my own coupler. So I borrowed some of my mom's sewing thread, which I'm shoving into the hole before pressing the coupler onto the motor. Now, theoretically I should do at least 3 pieces of thread equally spaced around the perimeter to kind of evenly shim the gap, but because of the close fit and the metal against metal parts, it ends up shearing off the thread half the time I try anyway, so I'm not gonna bother. I just want to take out the slack. Now, on the lead screw side of the coupler, which features the much more oversized hole, I ironically don't need to shim anything to get a good fit, because I simply ground the lead screw to be snug instead of the nominal 4mm diameter. But before I get it fully seated and the bearing pressed into the carriage, I need to screw on the Y-axis anti-backlash nut. And for that to be feasible, I think the laws of physics require it to exist beforehand. At least they did when I last checked. Here's the design I came up with. It's pretty simple, based on heat set inserts for brass thread, and it has a spring inside to eliminate backlash, just like the majority of zero backlash nuts out there. This time, I'm also not crazy enough to even try printing it on my DIY printer, considering the 4 plugs I did in the last episode took the better part of 2 entire days to print, film, and render the time lapses. After all, I do have a decent 3D printer upstairs. It's the Two Trees SP5 V3 I did a video about last Halloween. I don't think many of you guys even saw that video, which might actually be for the best since I couldn't exactly provide any valuable insights not knowing anything about 3D printers. In hindsight, I wouldn't exactly recommend that printer. It's okay mechanically, just a little overpriced for what it is, especially with competition like the A1 Mini that came out at around the same time. But with printer companies barfing out new models every other week like the smartphone industry, it's probably not even relevant talking about this anymore. Another reason I wanted to print this on the better printer is because the design inherently relies on parts sliding across layer lines, which really wouldn't work well at all with the rough surface finish I'm getting from inconsistent extrusions on the DIY printer. Finding long M6 threaded inserts was a real pain. These ones I ended up with are pretty underwhelming quality. The thread is in there crooked, and I have to chamfer them myself apparently. Yeah, that's not gonna cut it. See how much that bent the lead screw? Problem in this case isn't even the runout on the coupler as much as the fact that the shaft end I ground into the threaded rod doesn't have a consistent cross-section. It probably wasn't discernible on camera, but the geometry I ended up with here, rather than being a simple cylinder like you'd expect, was much more like this, with an almost round end, but going toward the shoulder where the threads start, it gets increasingly triangular, and while this shape easily fits inside a round hole, as soon as I tighten the grub screws, the triangular half gets smushed into the wall much more than an equivalent round cross-section would, and because the bottom actually is round, it bears on that first, tilting the whole thing, resulting in a bent screw overall because the coupler doesn't flex to compensate. The tolerances I'm working with here are absurd from a DIY woodworking perspective. I mean, this shaft's out of round by maybe 2 or 3/100ths of a millimeter, yet it totally ruined my day. So how do I fix this? Well, I don't think I can get around regrinding this end of the lead screw to get rid of the triangle, but given I've already tried my best, I seriously doubt I could achieve any better results with my manual grinding setup. So seeing as this is only one of a total of 5 thread rod ends I still need to grind to a smooth shaft, I, unbeknownst to you, spent the last couple days building a machine to take care of it for me. I really quickly cobbled it together out of scrap particle board from an old couch, hence why it's so rough around the edges, as well as some of the donated parts I have laying around. It's basically just the Dremel tool, height adjustable on a carriage with linear rails. This is driven by a stepper motor via a lead screw, all while a second stepper spins the threaded rod, which is mounted in bearings. This allows me to very slowly drive the running rotary tool into the threaded rod and end up with a totally round and consistent shaft end to the lead screw. Much better than anything I could have ever hoped to achieve by hand. That said, removing any substantial amounts of material with this machine does take significantly longer than doing it by hand did. Just look at this real-time footage. Oh, it's moving alright, just very slowly. Extremely slow, in fact. See? About the same speed as the minute hand of a clock. And this is actually a great time to remind you that you definitely do not have to go to similar lengths to manufacture parts outside of your capabilities. Unlike the name suggests, PCBWay doesn't just offer printed circuit board prototyping services, but also 3D printing, injection molding, laser cutting, and CNC machining and turning. And unlike me, they don't chicken out at stainless, but go all the way to titanium, which is notoriously hard to machine. So to them, stainless is just day-to-day life. Placing an order is actually really easy. You simply upload the CAD model for your part, as well as any potential technical drawings, select the material, tolerances, and surface quality, and you're good to go. PCBWay will task themselves with manufacturing the part to your satisfaction and get it shipped to you in a lot less time than it took me to build this crazy contraption and painstakingly grind those threaded rods, which shouldn't be a surprise since they have over a decade of experience to draw on. In fact, PCBWay are celebrating their 10th anniversary right as we speak, so happy birthday, I guess, and huge congrats on that milestone to the whole team from me. If you want to be in on the fun, they're having an event where you can get exclusive coupons, a special badge to add to your profile picture, support charities, and take part in a raffle. I already participated, so can't show you that anymore now, unfortunately. So anyway, I'll leave you the link in the description. Depending on when this video comes out, you might want to be quick as the event ends on August 31st. As always, big thanks to them for sponsoring this episode, and let's see if my machine did its job. Well, that was only about 8 hours of listening to the hideous whine of that Dremel, but the difference in the end result is like night and day. Fortunately, I remembered just in time to stick a dial indicator on it for before and after, and well, I was definitely taken aback by how bad it actually was. That's about 80 microns between the high and low reading, or almost 1/10 of a millimeter. Now, after redoing it with the machine, I'm down to under 20 in runout, under 15 even depending where I measure. I'm really happy with that, so time to put it back together. Of course, with the lead screw now down to 3mm, the 4.1mm coupler isn't gonna do anymore anyway, so I printed my own from PETG. You'll have to excuse, it looks pretty gnarly. My PETG is sopping wet, I don't have a filament dryer, and never properly tuned the filament profile. I really couldn't be bothered at first, and then it was suddenly too wet. I'm still rather new to PETG, okay? So the reason it had to be PETG is temperature resistance against the hot stepper, as well as the much higher layer adhesion obviously, and the weird hourglass shape makes it so it hopefully flexes a little bit without sacrificing too much strength for the press fit on the shaft. Oh, this is so much better. Now when I spin the lead screw, it barely wobbles. It's still not perfect, but you'll have a hard time finding an actually straight threaded rod at the hardware store. Okay, that should be the y-axis finally finished and ready to try out. I put some grease on the lead screw and wired up the stepper. Let's try it out real quick before I move on to the x-axis. And yeah, I guess it works. Great. Should be able to go a lot faster than this. It's currently set to half-step mode, so let me just undo that. We should be able to go faster. There we go. Yeah. Definitely doesn't run as smoothly as my 3D printer did, but that might be because everything's bigger and heavier as well. Sort of sounds like a washing machine when I go too fast, but that seems to be about maximum speed I'm getting. Just in case it wasn't obvious why my anti-backlash nut is attached to the carriage via this rather thin and flimsy tab instead of a decent mount, that's on purpose so the carriage gets decoupled from any wobbling the lead screw may do, and as you can see, this seems to work quite well. Anyway, great stuff, but as if this wasn't complex enough already, for the x-axis I have to grind no less than 2 threaded rods, because it's a linked dual screw system. After all, isn't it always best to make things as complex as humanly possible? That way there's a higher chance of suffering when it inevitably goes wrong, right? I built the machine such that I can install full 1 meter lengths of all thread in it. Just in case I mess it up, I can cut the ruined section off and have a fresh start, which obviously wouldn't be possible if I'd cut the screw to length first. And because I didn't have a 6mm ID pulley, there's simply a printed ferrule that goes inside an 8mm one. This also has the added benefit of being able to use the grub screws to tighten it without dinging up the lead screw threads. Because threaded rods are always a little undersized compared to their nominal diameter, I actually have to shim the difference using masking tape. Otherwise, the rod would wiggle around in the bearings and mess up the result. Having to press it in like this obviously makes setup quite involved, but the result's worth it, and without access to an actual lathe with a collet chuck, this is the best I can do. The reason for this little disc here is because the Dremel spins counterclockwise in this orientation and really likes to chuck all the metal shavings and grinding debris right at my ball bearing here, so just having a little gap between the rod and the bearing block isn't gonna do. Stuff is definitely still gonna get in there and ruin my bearing eventually. So the deflector disc screws right onto the rod to shield the gap and serve as a surface for the sparks to bounce off of. Also, you're probably wondering why I borrowed this controller to test my y-axis just now. That's because it's basically just 2 separate Arduinos and stepper drivers letting me control these motors independently via a potentiometer each. So if I twiddle this one, the spindle feed goes, and the other one spins the lead screw in either direction. Shout out to Patron Flo, who mostly rewrote the code I'm running on these a while back. Previously, the conversion from analog input to steps per second was totally unsmoothed, resulting in the motor speed sort of jittering, but now it's a lot better. And yeah, I probably could have gone the extra mile and fully automated this machine just so I wouldn't have to babysit it for hours manually controlling it while each pass only removes a couple dozen microns at best, but limit switches and firmware would have exponentially blown up the effort required for a trivial side quest like this. I'm still a rookie in programming, so I'm sure writing some dedicated code would have taken longer than just sticking through it the good old-fashioned way. All the silly talking about the machine you just watched was meant to replace a minute-long time-lapse montage of me sitting around watching the thing grind those rods, so here they are finished. Honestly, that stunt took way longer than I anticipated. 4 entire days to grind both ends of these 2 threaded rods to be precise. I kinda regret my statement at the beginning of the video.
I'm 95% done and just need to install the damn lead screw.
Yeah, that aged like milk. Anyway, since I don't have enough time to keep explaining every single thing for the remainder of the video without making it an hour long, please enjoy the build montage queued up in 3, 2... I just discovered something disastrous. The pitch on these 2 threaded rods is not the same. Did you know that can happen? And I'm not saying it's off by 0.1 millimeters over meter, that's obvious. I'm talking an entire millimeter per foot. For some reason, I only just now thought to check these against each other, and you can see if I push them together on one end, they very quickly stop meshing properly until actually the crests oppose each other, and they only get back in sync after about 13 inches, and this happens twice along the entire rod. I'm sure you can imagine just how bad this is on a dual lead screw axis. If I rotate these rods by the exact same amount, which will automatically happen since they're timing belt linked, even if I adjust the gantry to be square in the middle, move it to one side, and it'll be out of square by millimeter this way, and out of square this way by millimeter on the other side. And there is no way to fix it other than to just get an entirely new set of threaded rods, hopefully some more similar ones from the same batch at the factory, which I'm most definitely not going to do because grinding those ends to within plus minus 10 microns was a horrendous pain in the ass, which I have no desire to repeat whatsoever. And to anyone about to suggest I just drive these screws with separate motors to spin them at different speeds, just forget it. I'm never gonna be able to make that work software-wise because it's not supported by any firmware, at least none that I know of. So, as unfortunate as it may be, this is clearly as good a time as any to do the one reasonable thing I should have done from the beginning. That is, scrap the project in its entirety to go back to the drawing board and come up with a full redesign using NEMA 17s in a Core XY belt drive configuration. So that's what's going to happen. But not before I finish assembling that shit I just wasted so much of my time on in the promised montage. Just out of morbid curiosity if it'll actually fit together the way it was designed to. After all, I'm 99% there already, right? Right? And there you have it! It works just as well as I'd hoped it would. You can really see how much more effort I put into design and fabrication of the parts than on my 3D printer. The way these bosses on my anti-backlash nuts perfectly fit into the corresponding pockets on the carriages was just nuts. Pun intended. What a shame it's basically doomed. The effect of the dissimilar pitch of these screws is really noticeable now that they are linked, because I squared the gantry up to the frame back here, so front and rear of the y-axis are currently both 10mm from the left frame plate, but if I drive the carriage all the way over to the right, the front is 10mm away from the right frame plate as expected, but the rear actually 12. So the entire gantry is effectively 2mm out of square now, which is unacceptable. Now, it's not as if it was entirely impossible to fix this. I would just have to measure the exact pitch of these rods, and then I could print some special sized pulleys to spin both these lead screws at the exact speed ratio I need to ultimately move both sides of the X carriage by the same amount. That would be a nice challenge in and of itself, but unlike with my 3D printer where I was basically just trying to prove that I can make it work, here I promise to be more reasonable and just try to make a functional laser cutter. And in view of that goal, I have to say, dismantling it entirely and starting from scratch is definitely the reasonable thing to do, especially if I want to open source this design, which I kind of want to do, even though I don't really know why anyone would want to replicate this since there's already so many designs from more knowledgeable people than me out there. I'd have to redesign it anyway. So I think this is officially the new record holder for biggest failed project on this channel. And I'm gonna take the L. I'm a total idiot for not checking these threaded rods for accuracy before getting started. Especially since I knew they are inconsistent in diameter from converting my 3D printer to lead screws. Just double checking the pitch would have been the obvious thing to do. But I think in this situation the best thing I could do was basically what I just did. Make a video about it so other people can learn from my mistakes before investing resources and time into a similar project themselves. TLDR, if you want to build any kind of CNC machine with a dual lead screw axis using threaded rod, make sure to cut both lead screws from the same piece of old thread. I wonder what they did back in the day of these 3D printers. They used 4 threaded rods on the Z-axis, and I seriously doubt the stuff used to be more accurate back then. I also wonder just how mismatched the Z-screws on my own printer are, because I never thought to check there either. Anyway, thanks again to PCBWay for sponsoring this sort of failed episode, and really special thanks to everyone supporting on Patreon, helping to make video series like this where I can't necessarily make up some sort of egregious algorithm-friendly thumbnail for each installment more possible. I am realizing this series in particular doesn't seem to spark as much interest amongst my wider viewer base, but I hope you enjoyed and learned something from it nonetheless. I certainly did learn something. Enjoyed? Not so much. Bye bye!